Like with most sections in this chapter, we're going to be working with both exponential and logarithmic equations, which means there are different rules and processes to solving equations that are exponential and solving equations that are logarithmic. They're kind of parallel to each other in the ideas because they're inverse functions, so that makes sense. We're going to start off with exponential functions, which means we're looking at equations where the variable is in the exponent. There are two cases that we can see when we are solving exponential equations. The first one are when you notice that the bases are in the same power family. If they are in the same power family, we're going to rewrite the equation so that the bases are exactly the same. So you'd have like 7 to some power equal to 7 to another power. And if that's the case, then you can just take the powers themselves and set them equal to each other. Since these equations are 1 to 1, if the bases are the same, the exponents have to be the same. And once we do that, we just solve probably a linear equation and we get our answer. So for example, do you notice in letter A here, 2 and 16 are a part of the same power family? Because 16 is 2 to what power?
3.
4. Which means I could rewrite this one as 2 to the 3x minus 8 equal to 2 to the 4th power, because 2 times 2 times 2 times 2 is 16. At this point, since the bases are exactly the same, exponential equations are 1 to 1, which means those exponents have to also be the same. That's what an equal sign means. It means they are the same. So the bases are the same, exponents have to be the same. Well, that's a cute little linear equation that we can solve using skills from like 8th grade. We're going to add 8 to both sides, and we're going to divide by 3. So we get that the solution is 4. Make sense? The only way this type of equation can get more complicated is if the bases, both bases, have to be changed. Do you notice that 27 and 9 are both a part of the same power family? So let's rewrite them so that they exist with the same base. What power family are they a part of? 3. 27 is 3 to the 3rd power, and 9 is 3 to the 2nd power. So when I have 3 to the 3rd power, that's the exponent that's going to be multiplied by x plus 3. And 3 squared is going to be multiplied by x minus 1. Again, I'm just rewriting the bases. But whatever exponent I have to change that base with, I'm going to have to distribute into my exponent. Meaning, now that these big bases are the same, we just take the exponent, 3 times x plus 3, and set it equal to 2 times x minus 1. If the bases are the same, the exponents are the same. This is now a linear equation, and when we solve linear equations since forever, we're going to distribute, then combine like terms, and use inverse operations. This becomes 3x plus 9 equal to 2x minus 2. I'm going to move all of the x's to the left side and all of the regular numbers to the right side. So if I subtract 2x from both sides, I end up with just regular x. And if I subtract 9 from both sides, I end up with negative 11. If you needed to do that one in 2 steps, that's totally fine. So again, our first case today is when the bases can be written in the same power family. If, however, the bases cannot be written as the same power family, we're going to have to use different steps. What we're going to do is we're going to make sure the exponential expression is isolated. So the only thing on usually the left side of the equation is the base with the power. We're then going to take the natural logarithm on both sides of the equations, or a common logarithm if it's base 10, and use the properties of logarithms we learned from last class to isolate the x and finish solving. So for example, do you see how 4 and 15, they're not a part of the same power family? So what we're going to have to do is isolate the thing with the power. Don't draw this box, but just watch. You see how 4 is the base? And 4 to the x is completely by itself. We're good to go. It's isolated. At this point, we take the natural log of both sides. We're going to do the natural log of 4 raised to the x power equal to the natural log of 15. what we do to one side, we do to the other. So we're taking the natural log of both sides. Now, last class, we learned about a property of logarithms that's going to allow me to do something different with this exponent of x. What can I do with it?
Put it to the front.
Put it to the front. Nice. So if we go drop that in front, this is now going to say x times the natural log of 4 equal to the natural log of 15. Now remember, our end goal is to get the x by itself. So what do I have to do on both sides to get x by itself? Divide by the natural log of 4, which means this would be x equal to the natural log of 15 divided by the natural log of 4. If the question were to ask you to write it in terms of logarithms, you would type that in. You would answer with this. If it asks you for a decimal approximation, this is where we turn to our calculator. Now for me, unless the book says otherwise, I'd like for you to round to 4 decimals because I teach AP Pre-Cal and I'm so used to doing that. So 4 decimals, please. But we're going to take our calculator and do natural log of 15, close parentheses, divided by natural log of 4, close parentheses. If you don't have your calculator, go grab it real fast. Once you type that in, you should get that x is approximately equal to 1.9534. Do y'all agree? Nice. So again, this is a decimal approximation. If it says answer in terms of logarithms, you just stop like the step before you would plug it into your calculator. Can we try another? Great. Let's look at question D. Again, 10 and that number, 120,000. Not a part of the same power family. So we're going to make sure the base and the power is isolated. Is the base with the power by itself? Yeah, okay, so we're good to go. We're going to take the logarithm of both sides. Typically, you would take the natural log of both sides. Why in this problem would I want to take the common log of both sides? Because it's base 10, and what is the base of a common log? 10. So that's nice. We're going to make that happen. So we're going to this time do log, and I'm going to show the base 10. Log base 10 of x equal to log base 10 of 120,000. You don't have to show the base 10. I'm just making a point. Because hopefully your spidey senses are going off. Log base 10 of 10 raised to the x power. What happens to the log base 10 of 10? We don't even have to do the other exponent property if we use that basic property there. So I, in my calculator, can just type in what is the common log, that's a button, of 120,000. If this question asked in terms of logarithms, this is how we would answer. But it's going to ask you to round to 4 decimals, so x is approximately equal to, should be 5.0792. Make sense? Okay. Now I'm going to make them a little bit harder. Don't panic though. Remember, our goal when we have a complicated exponential equation, this time maybe draw this box, is to make sure that the base with the power is by itself. Just the base with the power, no coefficient, no plus or minus behind it. We want just the base with the power to be by itself. So if I want to get that little box by itself, what should I do first to isolate it? Add 3 to both sides so that this becomes 40 times e to the 0.6x equal to 240. Again, if I wanted just the base with the power to be by itself, what would I do next to isolate? Divide by 40. Now, as a heads up, this step, if you divide 240 divided by 40 and you got a decimal that you'd have to round, make it a fraction. This one does turn out pretty. 240 divided by 40 is just 6. But if that had been 6.5832, whatever, and you'd have to round it, you give me back the fraction. We want to keep our numbers as accurate as possible in the middle of the question. Now, is the base with the power isolated? Nice. We take the natural log of both sides. I'm going back to natural log because I only use log when it's base 10. So if I take the natural log of e to the 0.6x, that'll be equal to the natural log of 6. Is anybody's spidey senses going off here? What's the base of a natural log? E. So log base E of E, just like the log base 10 of 10, that's going to cancel out again. That's nice, because then I only have 0.6x equal to the natural log of 6. And so if I solve for x, this would be x equal to natural log of 6 over 0.6. If it asks for in terms of logarithms, this is where we would answer. But if it asks for a decimal approximation, you go to your calculator, you type this in. Make sure you close that parentheses before you go to the divide. We should get that x is approximately equal to 2.9863. Questions, comments, concerns on this one? Because we had to do a few steps before we got to the natural log section. Do we follow those steps? Okay, so far we have seen two kind of plain examples where we didn't have to isolate the base and the power. We've seen one example where we have to isolate the base and the power. But look what's happening in number F. There are two bases and powers. Interesting. Let's just focus on one of them. If we focus on the base of 5, is the base of 5 isolated? Yeah, it's as isolated as it's going to get. I know the other side also has a base and a power, but we're not going to panic. We're immediately going to go to the natural log step. If we take the natural log of both sides, this is the natural log of 5 to the x minus 2 equal to the natural log of 4 to the 2x plus 3. By the way, I don't know why sometimes I write it in print and sometimes I write it in cursive. There's no reason, in case you were wondering. Just bad habits. Okay, we go back to the properties of logarithms. We have these exponents. What can we do with them? Put them in front. Now, when you put them in front, please put them in parentheses because they're a binomial. So we're moving those exponents to the front. This becomes x minus 2 times the natural logarithm of 5 equal to 2x plus 3 times the natural logarithm of 4. We just drop them in front, just like we did last time. Now, if we notice, I know there's logarithms there, but they're just numbers. We have x's that need to be distributed by the scalar outside of the parentheses. This is a linear equation. We go back to linear ideas. We are going to distribute the natural log into those parentheses so that we can get the x's out of the parentheses. This would become x times the natural log of 5 minus 2 times the natural log of 5 equal to 2x times the natural log of 4 plus 3 times the natural log of 4. We just distribute it. Our end goal when we're solving equations is to get x by itself. Take a highlighter. I'm going to use yellow. And I want you to highlight the two entire terms that have x's in them. So that would be x times the natural log of 5 and 2x times the natural log of 4. This is just to bring our attention to these terms. Those are the two terms that have x's in them. We need to get the x's on the same side of the equation so that we can eventually get them to be a single x. So what I'm going to do is I'm going to move this yellow term to the same side as this yellow term. And then since this doesn't have an x, I'm going to move it to the other side. This is just inverse operations. If this was positive 2x natural log of 4 on the right side, when I move it over, what will happen? It will become negative, correct? So this is now x natural log of 5 minus 2x natural log of 4. And when I take that 2 natural log of 5 and I move it to the other side, what does it become? Positive. So now I have 3 natural log of 4 plus 2 natural log of 5. Okay, the x's are on the same side. This time with your yellow highlighter, I want you to only highlight the x, not the term, just the x. Remember, our goal is to solve for x to get it by itself. Do you see how both terms on the left side of this equation have an x in them? As if they're both divisible by x. What we're going to do is we're going to factor out the GCF of these two terms, and the GCF of these two terms is simply x. we took those 2 yellow pieces and took them out, wrote them in front of a parentheses by itself, which means the leftovers would be natural log of 5 minus 2 natural log of 4 equal to 3 times the natural log of 4 plus 2 times the natural log of 5. Do we follow that step? We took the x's out, boop, factored them, put them in front. It looks super complicated, but we're 1 step from being done. Because our end goal is to get x by itself. What can we do on both sides to get the x completely by itself? Divide. Now if we divide the entire numerator, 3 times natural log of 4 plus 2 times natural log of 5, and we divide that by natural log of 5 minus 2 natural log of 4, we have isolated the x value. If it asks for this answer in terms of logs, this is what you return as an answer. But it will probably ask for a decimal approximation. So we go to our calculator and we make sure we close all of the parentheses for all of those natural logarithms. Good luck. You got this. We should theoretically get that x is approximately equal to negative 6.3429. The second function type that we're going to be looking at solving today are logarithmic equations. Just like with exponentials, there are 2 cases that we need to be looking for. The first one is when there is a logarithm only on one side. If there is a logarithm only on one side, we're going to condense the equation to a single logarithm using properties of logarithms or inverse operations so that it is plain log base b of a. Kind of like how we had to isolate the base with the power, we need to isolate the logarithm. Once we have it as log base b of a equal to c, we're going to use the log loop to rewrite it as an exponential. Once it's in exponential form, the x will not be in the exponent anymore, and we can solve for x. It is very important, though, that we look at this step 4. Step 4 is something that you have to do. This is not like your math teacher telling you, you should check your work, although you should always check your work. This is the fact that logarithmic equations have restrictions on their domain. So occasionally you're going to get an answer that you have to throw away. So you always want to look back and check your work to make sure it is an allowed value for x. It's very simple to actually do this, and we can pretty much do it in our head. We don't have to show our work here, but we do need to make sure we are checking our work. So for this first example right here, example A, do you see that there is only one logarithm on one side? So if logarithm's on one side and it's already by itself and isolated, all we're going to do now is log loop. What's the base of that logarithm? 4. If I was log looping, what would be the new power? 2, and that should be equal to x plus 3. We've gotten the x out of the exponent. Now we can solve for it. By the way, what is 4 to the second power? 16. So this is just 16 equal to x plus 3. And 1 step to solve for x? Minus 3 on both sides. Very good. So we get 13 equal to x. Now we box our answers, but we don't get too excited. We always check our work. And by checking our work, what I mean is you're going to take this value of x and just plug it in to the inside of each logarithm that's in this problem. What is 13 plus 3? 16. As long as the number you get when you plug this in right here is a positive number, you're good. So is 16 a positive number? Yes. We're good. If you get a negative number when you plug in your potential answer choice, that's when you have to throw it away. And you're only plugging it into the arguments of the logarithms, not into the entire equation, just the arguments where the domain restriction would be. Let's look at question B. I see that there is only one logarithm, but it is not isolated. It's not by itself. What do we have to do to get this natural log by itself? Divide by 3. So if I divide both sides by 3, I'm left with natural log of 2x equal to 4. And now that the natural logarithm is by itself, and there's only one of them, we're going to log loop. What's the base of that logarithm? E, which means now this should be e raised to the 4th power equal to 2x. That's the log loop. Remember, our end goal here is to solve for x. So how do you get that x by itself? Divide by 2. So if I was giving an exact answer, which is what you might see this referred to as an exact answer, Or you might see that referred to as an answer in terms of E. Again, an exact answer or an answer in terms of E. This is where you would stop, but E is a number, so we can also go to our calculator and get a decimal approximation. You're going to do second divide, raised to the fourth power, divide by 2. You should get that this is approximately equal to 27.2991. Agreed? Nice. Okay, example C on here is still this first case. We don't have to look at the second case yet, because do you notice that there are only logarithms on one side of this equation? There are 2 of them, so we're going to have to deal with that. But since the one side of the equation just has a plain number, this is still the first case. We need to condense these logarithms using the property of exponents. What? Properties of logarithms. To condense them down to 1 to make sure it's isolated. Okay, thinking from last class, how do you combine 2 logarithms that are added together? Multiply. So we're going to write this as a single logarithm. Log base 2 of x times x plus 7 equal to 3. Now last class we would have left this logarithm looking like this. Today, unfortunately, you are going to have to simplify those arguments when possible. So I actually do want us to go ahead and distribute this and make it x squared plus 7x. Okay. Now that the base is isolated and there's only one logarithm, we can do the log loop. What's the base? 2. This should be 2 to the third power equal to x squared plus 7x. 2 to the third power, don't say 6. What is it? 8. So now if I think about this and I have all my exponents taken care of when I can evaluate, what kind of equation did we just make here? Quadratic. How do we solve quadratics? Set it equal to 0 and we hope that it factors. And if it doesn't factor, we use the quadratic equation. But if we set this equal to 0, that means I'm subtracting 8 from both sides. And so I'm left with x squared plus 7x minus 8. Let's hope this factors. Is there something that would multiply to negative 8 and add to 7? 8 and 1. So this would be 8. This one would be 1. Which one's positive? Which one's negative? Say is 8 is what? Positive? Agree. If that's the factored form of this quadratic, then the solutions are negative 8 and positive 1. We've solved for x. We're good to go. Except that we have to check our work. In every logarithm you do need to go back to the original problem and see if plugging the new proposed solution in would make the argument negative. If I put negative 8 right here, would it make the argument negative? Yeah, even especially here. So negative 8 plus 7 is still negative. We have to throw negative 8 away. Goodbye. It's not actually an answer. Now we check 1. If I plug 1 in right here, that's positive. If I plug 1 in right here, that's positive. So 1 is actually okay. Letter D is a different case. What do you notice is now on both sides of this equation? True. What else? There's logarithms on both sides. That's our second case for logarithms. When there are logarithms on both sides, this one's actually kind of easier. You're going to condense the equation on each side so that you have a single log on the left and a single log on the right using properties of logarithms. You're then going to use the one-to-one property of equations to rewrite log base b of a equal to log base b of c just as a equal to c. Just like when the bases match, we made the exponents the same. When the logarithms match, you make the arguments the same. We'll then solve for the variable as necessary and then make sure that we do the step 4 again, because anytime we have a logarithm, we must check our work to make sure that we don't have to throw any of them away. All right. We need to condense these logarithms so that there's a log on the left and a log on the right. How do I combine these that's the left side, these left side logarithms into one? Divide. So we're going to divide those logarithms. This will be the natural log of x plus 2 over 4x plus 3 equal to the natural logarithm of 1 over x. Since now we have the logarithms being the same, all we do is take the insides out and we solve the arguments set equal to each other. This is x plus 2 over 4x plus 3 equal to 1 over x. We've now created a rational equation, or since that equal sign is in between these two fractions, we've created a proportions question. How are we going to solve this proportions question? Cross multiply and see what we make. So if we do this cross multiplication, this would be 1 times 4x plus 3, kind of unnecessary since it's multiplied by 1, but I'm going to write it anyways. And we'd have x times x plus 2. We just cross multiply these fractions. I'm going to distribute, so this would become 4x plus 3 equal to x squared plus 2x. Again, what kind of equation have I created? Quadratic. We go back to our quadratic skills, which is to set it equal to 0 and solve. So this would become 0 equal to x squared minus 2x minus 3. Whoa, where'd the minus 3 come from? Or minus 2x come from? Yeah, 2x minus 4x gives me minus 2x. Once it's set equal to 0, we hope that it factors so that we don't have to use the quadratic equation. Are there factors that that factor this quadratic? Things that multiply to 3 are 3 and 1. Which one is positive? Which one is negative? 3 is negative, 1 is positive. Which means my solutions are x equal to 3 and x equal to negative 1. But before we call it a day, we check our work. If we plug 3 into the original arguments, what is 3 plus 2? 5 is good because it's positive. What is 4 times 3 plus 3? 4 times 3 is 12 plus 3, 15. Positive though. We're good. 1 over 3, is that positive? We're good. So 3 is good to go. Now we plug in negative 1. Is negative 1 plus 2? 1. That's a positive number, right? Okay, we're good. How about 4 times negative 1? Plus 3. Now we have a negative 1. Can we leave this as an answer? No, we have to throw it away. It almost worked. It did not work in every argument, so you throw it away.